In this video, we are going to derive the formulas for third order non-homogeneous ordinary differential equations. If we want to solve them with variation of parameters, we can use the formulas that I talked about at the end of the video for the derivation of for the formulas of second order associated with second order ODEs. But I wanted to show you how to solve third order ODEs, and I didn't want you to have to rely on this sort of like analogy principle that if this is how it works for second order ODEs, this is how it would work for third order ODEs, and say, oh, that's kind of expected. That's what I think should happen. But we don't want to have to rely on that. So I'm going to show you where the formulas come from. So let's say you've got a second or a third order ODE that can be written this way. You've got y triple prime plus p of x times y double prime plus q of x times y prime plus r of x times y, and that's equal to f of x. Suppose that that's your differential equation. Then in that case, assuming that y1, y2, and y3 are solutions to the corresponding homogeneous equation, this is your linearly independent set of solutions, that fundamental set of solutions. The corresponding homogeneous equation, and that looks just like this, where the right-hand side is equal to 0. And of course, these functions p, q, r, and f are known. And f is not the 0 function. It's not equal to 0 all the time. So this is a non-homogeneous differential equation. Then in that case, we would assume that y sub p is equal to u1 y1 plus u2 y2 plus u3 y3. For some non-constant functions, u1, u2, and u3. Well, then if we take the first derivative, we get this. By the product rule, we have the derivative of the first times the second plus derivative of the second times the first. Actually, I'm going to shift to using color for those derivatives. Then here we'll use the product rule again. We have derivative of the first times the second plus derivative of the second times the first. And then we're going to add derivative of the first times the second plus derivative of the second times the first. Now at this point, we could just differentiate again and then differentiate again and differentiate again. But later we're going to make some assumptions so that we can come up with 3 equations and 3 unknowns. That's normally how this is done. That's how I did it in the derivation for the formulas for second order ODEs. But rather than doing that, which leads to quite a long differential equation with just so many terms, I think we end up with a lot of terms for y triple prime, and then quite a few for y double prime, and then y prime. I mean, it's a lot. I'm going to make the assumptions as I go. So one of the assumptions that we're going to make later, and that will simplify things for us, is that this is true. We want to assume that u1 prime times y1 plus u2 prime times y2 plus u3 prime times y3 is equal to 0. If we make that assumption, that simplifies this quite a bit. It gets rid of 3 of our 6 terms. Then under that condition, we've got u1 y1 prime plus u2. So these guys have been taken care of. This one, and this one. I've got u1 y1 prime, and then this should be a u2. u2 y2 prime, and then I've got u3 y3 prime. Okay, now we're going to take the derivative again because it's a second order differential equation or a third order differential equation. So we have to keep going. So under this assumption, and we want to keep track of those assumptions, so I'm going to put this in a box. We end up with y sub p prime is equal to this, and therefore y sub p double prime is equal to the following. Using the product rule, we'll have derivative of the first times the second plus derivative of the second times the first. And then we have the derivative of the first here times the second. And then we're adding the derivative of the second times the first. And then we add derivative of the first times the second. And then we add derivative of the second times the first. Now, if you're wondering why can we make these assumptions, or why are we making these assumptions, it's because eventually we're going to end up with a differential equation. It'll be a third order differential equation. And it will involve the first, second, third, and third derivative of u1, u2, and u3. So since we don't know u1, u2, and u3, we'll have one equation with 12 different unknowns. One way that we can simplify that equation so that we don't have so many unknowns is by making assumptions like this. And that those assumptions will help us, because basically what it's going to do is it's going to take that one equation with 12 unknowns and eventually get us down to 3 equations and 3 unknowns, which is what we want. Because once we have 3 equations and 3 unknowns, we can use Kramer's rule to solve. Now, when we're choosing these equations, what I'm hoping for is a system of differential equations for u1 prime, u2 prime, and u3 prime. So when I'm deciding which terms to add together and set equal to 0, I'm including those that include the u1 prime, the u2 prime, and the u3 prime. So when we take the second derivative of this guy after making this assumption, so now we had 3 terms here after that assumption, so now we've got 6 terms here. We're going to make another assumption. I'm still going to take out all the terms that involve u1 prime, u2 prime, and u3 prime. So there's one, and there's one, and there's one. So we're going to assume that the sum of those is equal to 0 this time. And again, the reason for that is because we want 3 equations and 3 unknowns involving u1, u2, or u1 prime, u2 prime, and u3 prime as our unknowns. Now the assumption is that we know y1, y2, and y3, so we can compute these derivatives. These are known functions. So I'm assuming these guys are 0. So I've got one equation with 3 unknowns here. Then I've got another equation with the same 3 unknowns. So now I've got 2 equations and 2 unknowns. And I'd really like to have 3 equations and 3 unknowns so I can use Kramer's rule to solve it. So that's what we're going for. We're 2/3 of the way there. So now under this assumption, y sub 2 or y sub p double prime is equal to this. Oops, I forgot to write my u sub 3 there. Now let's take the derivative again. We have derivative of the first times the second plus derivative of the second times the first. And I forgot to use my color. That was these guys. I'll do the same thing here. Derivative of the first times the second plus derivative of the second times the first. And then here we have derivative of the first times the second plus derivative of the second times the first. Okay, and let's not make any assumptions about this guy yet. Now let's substitute all of these into the differential equation. So the ones that I'm substituting are the simplified forms of y sub p prime and y sub p double prime and then y sub p triple prime. So I'm assuming that this is my y sub p. That's what I'll substitute into the differential equation. And this is the simplified y sub p double prime under our assumption, or y sub p prime, excuse me. And then this is the simplified y sub p double prime under that second assumption. And the third derivative, we're not simplifying yet, but we've got that as well. So we're going to substitute all 4 of these guys into this general form of that third order differential equation. So we have y sub p triple prime, which is this. I'm just copying it again. It's really easy to lose a prime or accidentally write the wrong subscript. I'm going to be careful. Try not to do that. It's the type of mistake I tend to make. Nothing wrong with that at all. Okay, so we've got y sub p triple prime, and then we're adding p of x times y sub p double prime. So I've got p of x times this guy. And then we're adding q of x times y sub p prime. So that's q times this guy. And then we're adding r times y sub p. And that's equal to f of x. Okay. So we're here now, and we want to group terms involving the U1, U2, and U3. So I'm looking for terms that just have a U1 in them. And it looks like I've got one right here. And then I've got one right here, and one right there, and one right there. So I'm going to group these, and I'm going to factor out the U1. So I've got U1 times all of this. So it's y sub 1 triple prime plus p of x times y sub 1 double prime times that U1, which I factored out, plus q of x times y sub 1 prime plus r times y. So that's right there. Now, y sub 1 was a solution to the corresponding homogeneous equation. So if I plug this in over here, I'm going to get 0, because that's what the corresponding homogeneous equation is. So these terms are all gone because y sub 1 is a solution to that differential equation. Similarly, I want to group all the u sub 2 terms. I've got a u sub 2 term here, and another one here, and one here, and one here. So we're adding u sub 2 times, I bet you can guess what's going to happen, y sub 2 triple prime plus p of x times y sub 2 double prime plus q of x times y sub 2 prime plus r of x times y sub 2. And y sub 2 was a solution to the corresponding homogeneous differential equation. So if you substitute this in, y sub 2, into the left-hand side of this differential equation, you're going to get 0, because that's what it means to be a solution to the corresponding homogeneous equation. So we get that. And I bet you can imagine what's going to happen next. Let's look at the u sub 3 terms. I've got one here, and one here, and one here, and one here. I factor u sub 3 out from that. We get this. Y sub 3 triple prime plus P of x times Y sub 3 double prime plus Q of x times Y sub 3 prime plus R times Y sub 3. And that's all times U3, but I've factored out the U3. And that is the left-hand side of the differential equation evaluated at Y sub 3. So that's 0. So what ends up being left over is this U1 prime plus, or this U1 prime term, this U2 prime term, and U3 prime term, and then everything else has been covered except for the f of x. So what we end up with is U sub 1 prime, y sub 1 double prime, plus U sub 2 prime, Y sub 2 double prime. That's that one plus that one, plus that one, plus U sub 3 prime times Y sub 3 double prime is equal to f of x. That's pretty nice. So this equation simplified to this equation at the very bottom, because all of these other pieces are 0, because y sub 1, y sub 2, and y sub 3 are solutions to the corresponding homogeneous problem. Now, getting here would have been a lot harder if we had not have made these assumptions early on. So we made these assumptions. We said that this equation involving u1 prime, u2 prime, and u3 prime must be satisfied. So that's one equation with 3 unknowns. And then I've got another equation with the same 3 unknowns. Remember, y1, y2, and y3 are known, so their derivatives can also be computed pretty easily. And then lastly, I've got this. And the unknowns are u1 prime, u2 prime, and u3 prime. So we actually have a system of 3 equations and 3 unknowns. And they are u1 prime y1 plus u2 prime y2 plus u3 prime y3 equals 0. And then our second assumption was, u1 prime y1 prime plus u2 prime y2 prime plus u3 prime y3 prime equals 0. And then because y1, y2, and y3 were all solutions, it turned out that u1 prime times y1 double prime plus the corresponding terms for u2 and u3, you're going to have exactly that same form. If you add those together, then you have to get f of x. And that's pretty nice, because now we can use Cramer's rule to solve this, and we can get u1 prime, u2 prime, and u3 prime by themselves. Okay, so we've got this system of 3 equations and 3 unknowns, which we can solve using Cramer's rule. In order to do that, we'll rewrite it this way. Oops. I'm going to write it as the product of a 3 by 3 matrix and a column vector with 3 entries. Now the coefficients go here, and the unknowns that we're solving for go here. Our unknowns are u1 prime, u2 prime, and u3 prime. The functions that go in this column vector are 0, 0, and f of x. And the coefficients are y1, y2, and y3. And then we've got y1 prime, y2 prime, and y3 prime. And y1 double prime, and y2 double prime, and y3 double prime. So this times this equals that. And notice that that matrix, when you take its determinant, that's the Wronskian of those 3 linearly independent functions, y1, y2, and y3. Now Cramer's rule says this: if you have a 3 by 3 matrix, Let's say the entries are A, B, C, D, E, F, G, H, I. And then I've got J, K, and L over here. Then X can be found by computing two determinants. Now this is provided that the determinant of this matrix is not 0. That just means that those equations that correspond to this matrix multiplication, AX plus BY plus CZ equals J, DX plus EY plus FZ equals K. And then this dotted with this equals L. If this determinant is non-zero, what that means is that those equations are not redundant. There's no equation on the list that's telling you either what one of the other equations tells you or what a linear combination of the other two equations would tell you. So that means that this system of three equations with three unknowns, x, y, and z, has a single solution if the determinant of that matrix is non-zero. So we'll find the determinant of that matrix that goes in the denominator. And then in the numerator, you're going to take the same matrix, but you're going to replace that first column with I, J, and K. And that's going to give you the X value, that first variable. And similarly, you'll take the same determinant, that's going to go in the denominator when you're calculating Y. But here with Y in the numerator, you're going to take that determinant and you're going to swap out this column for I, J, and K. And again, I, J, and K is that right-hand side. And then if you want to find Z, you do the same thing. Since this is our third variable, we leave the first two columns alone. And we swap out that third column for I think I wrote I, J, and K. It's J, K, and L, based on what I did up there, sorry. J, K, and L, J, K, and L. Okay, sorry, it's a little bit messy, but I hope you get the idea. This vector here is that column vector over there. Now, this is called Cramer's rule for a system of three equations and three unknowns. What we're doing here is the same thing. We're just going to apply Cramer's rule to find U1 prime, U2 prime, and U3 prime. So U1 prime is our first variable. And the determinant of this matrix, we label that W. That's the Wronskian of the three linearly independent functions, Y1, Y2, and Y3. So that's really nice. Since they're linearly independent functions, you know that that's non-zero. So you know you're going to be able to solve this system of equations for U1 prime, U2 prime, and U3 prime. Then in the numerator, you leave the second two columns, alone. And you swap out that first column with 0, 0, and f of x. We call this matrix W1. To find U sub 2 prime, we do the same thing, still have that Wronskian in the denominator. But since it's the second variable, we swap out the second column for 0, 0, and f of x. We call this matrix W2. So we've got W2 over W here. And then U sub 3 prime comes from doing exactly what you would expect. You leave the first two columns alone. And you swap out that last column with 0, 0, and f of x. Okay, now remember what the goal was. Our goal is to find y sub p. And we said that y sub p has this form. It's u1 y1 plus u2 y2 plus u3 y3, where y1, y2, and y3 are known functions. You've already found them. You can find their derivatives. You can find their second derivatives. You can even find their third derivatives. But we just don't know what u1, u2, and u3 are. Well, going through this procedure allowed us to find a system of 3 equations and 3 unknowns that u1 prime, u2 prime, and u3 prime must satisfy. So now we can take these and anti-differentiate them to get u1, u2, and u3, which is what we want, because we're going to multiply u1, u2, and u3 by y1, y2, and y3 and add those together to get y sub p. So u1 will be the antiderivative of w1 over w. And u2 will be the antiderivative of w2 over w. And u sub 3 will be the antiderivative of w3 over w. And then y sub p is u1 y1 plus u2 y2 plus u3 y3. And the general solution is y equals y sub c plus y sub p. So you'll have a constant times y1 plus a constant times y2 plus a constant times y3 plus u1 y1 plus u2 y2 plus u3 y3. And this will work for, well, whatever the domain is of all of these functions. Like, you have to look through the method and make sure that all the functions are well defined, and every step in the method follows logically from the one before it based on your previous assumptions. Here we'll let the constants of integration be 0, because we're going to take these and multiply by y1, y2, and y3, and we already have constants times y1, y2, and y3 as part of y sub c, so we don't need them from y sub p. And that's how we get the general solution. So in the next video, I'm actually going to solve a third order differential equation using variation of parameters. But in that case, I'm not going to go through the derivation. I'm not going to go through and make these assumptions. I'm just going to say, let's let y sub p equal this. Then by variation of parameters, u1 prime, u2 prime, and u3 prime have these forms, and then we'll just compute those 4 determinants, use them to find those derivatives, anti-differentiate to get the u's, and then multiply them by y1, y2, and y3 to get y sub p. So I'll see you for that in the next video.